All right, guys. So afternoon. So you see how fast we get through this time. We all labs and stuff to go. So the stuff I wanna get done, the time we have, I wanna go back through the Ampere circuit law. I wanna go through reluctance and how it changes, the BH curve, and a air gap question. All right, and we'll see how it goes. So I think I introduced this to you all last week. It's called Ampere circuit law, so we'll have went more in depth. We really had to know the in-depth stuff. All you had to know is when you cannot apply the law. Yeah, that is all you had to remember. That is all, because you're gonna use it in questions, right? And it's a very important and foundational equation that will take you well into this course. And the rest, if you want to do power and tree and stuff, right? So it's Ampere circuit law, and the law just states that it just relates magnetic field and current. Yeah. So and the thing I want you all to remember when you're using the Ampere circuit law, you may be asking, well, how will I know when to apply it? You can apply it in most loops. Come on, a magnetic field is like this, and you have a coil wrapped around it, and then a secondary coil. Right. Ampere circuit law will apply once you have a closed loop. Keywords being a closed loop of electric current. So, like if I have, let's say I have a coil like this. Yeah, I cannot apply amperes to self a coil. I cannot use amperes circuit law here because I have a air gap. Yeah, which means it's not a closed loop. Yeah, it had to be wherever coil it is, no matter where. So to go around, and it mustn't change material or anything. Yeah, you have to stay in the same material. So if this is iron, everything had to be iron. Have to be a closed loop. Yeah. Once it's a closed loop of the same material, it could go out, which is what I showed you now with the torus and all those stuff. He will have showed you materials where, oh sorry, cores where it's just one material, a coil, and he asked you to do calculations. And yeah, but now as you continue in the course now, he will start to give you air gaps. Yeah, and when you have an air gap, or if you have a composite core is basically a core that's made up of multiple core materials like cast iron, steel, and all those stuff is different materials. Yeah, so when you see different materials or air gaps which break in a closed loop, you can't use Ampere circuit law. Right? So Ampere circuit law, HL is equal to NI. Yeah, where H is the field intensity, N is the number of turns, I is the current, and L is the length of the flux path, which by now you all know goes to the center or the mean diameter of the material. Alright, so that's something to keep in the back of your mind, right? So, and the second thing, if you all didn't know what permeability is, think think of permeability as the ability of a medium to allow flux through it. So if you all don't know what flux is like those straight lines that will be seen in materials. Yeah. Remember, flux is like current, but for magnetic systems. Yeah. So this here is flux. Different mediums will be more reluctant to flux going through it. Yeah. Cast iron, steel, all those material will be less and more reluctant to flux moving through it. Right? The material or the medium that has the worst or the highest reluctance is air. Air do like magnetic flux going through it. Yeah. So the permeability of free space or air is very high. Okay. And there's something nice to remember. So the symbol for this is mu. I think you should know that by now. So mu is inversely proportional to reluctance. So if you increase the reluctance, by default, you decrease the permeability. But really and truly, this is related to the core. Yeah. So if for higher permeability, so if I increase this, reluctance will decrease, which makes sense because if a material less, um, say, sorry, if a certain material have a higher permeability, that means reluctance or flux can't go through it as easily. Yeah. So, but if it have a low permeability, it will allow it to go through easy. Yeah. So there's something to remember. All right. So a little equation you could remember. All right. So we went through the Ampere circuit law. Now I wanna go through deriving different pieces of it. So by now you all should have this formula sheet, right? You all should be memorizing your formulas. You should have no reason to not know your equations, right? So let me just derive some forms of the Ampere circuit law, right? So I go back to this, I have a whole page. So I write it. So I want this, it's real cool. And if you remember this, most questions are real simple. So this is real important to pay attention. So HL is equal to NI. Yeah, I could plug equations into this to get other forms of the equation. Yeah, so F or magnetomotive force is Ni. Yeah, also F is equal to phi R. Yeah, so from these two, we could just plug this part. Oh my goodness, into it. And you could get this. So you get HL is equal to F, that is one, because F is Ni. So depending on what they give you any question, you could go anyway. Yeah, that's the goal I'm trying to get. What else you could go? For this, HL could be equal to phi R. R is reluctance. This is flux, right? And next thing, B is equal to mu H. So I could transpose this for H and get B and mu and plug it back into this. So I'll get B L on mu is equal to phi R. Yeah, and I could go again and again. R as an equation is L Ni and R, sorry, mu, L and mu A. Yeah, so you can plug that into the question equation again. So you gotta go again. L and mu A. Yeah, and just have an equation too, and you can go again and again and again. One way to catch is once you know your equations, it don't matter what they give you in the question, you could get the answer. It don't matter what they give you. Once you know your equations, you just plug in equations into other equations. Yeah, and after you get accustomed with the equation of some that asks for inductance, you already have base equations in your head for inductance. Yeah, so depending on what they give you, you can find the answer real quick. Compared to somebody that has a limited scope of the equations, they will struggle to find the answer. Yeah, so in this course, make sure you know your equations and make sure you know the laws and stuff when you could and when you can't apply. Yeah, so that's something to jog in mind. Notice so just equations I use. So I just plug equations into other equations. Yeah, so example, a circuit law. And it's only applicable for closed loop. In the closed loop, it can't have any gaps and it must be the same material. Yeah, once you remember that, you'll be able to apply it. Right, and it's a cool law to know, honestly. All right, so let's get to the answer. Reluctance. All right, how reluctance could change. So any materials that so gave you by now, the material itself was one type core, meaning it had no air gaps. It didn't have changes in materials and all of that, right? So what could cause reluctance to change? Well, the L, the length of the core parts, could cause the reluctance to change. So if I draw a core, so there's a core, and we know it does go to the center. Yeah, so what could cause reluctance? Yeah, the length. If the length change, the reluctance will change. Yeah. A, think of A as the cross-sectional area of the material. So if I look at this material from above, it will look like that. Yeah, so this here is once it's a uniform shape, that will be the area. Yeah. If that increase, in this case, it's inversely proportional. So if this decrease, the reluctance will increase. Yeah. And then, so length, if length change, the reluctance will change. If the area change, the reluctance will change. And the last thing is this here. This here is with respect to the material, because all materials will have a different relative permeability. Yeah. So that's us. If the material different, you can't use Ampere circuit law. Why? Because you'll have a different reluctance, so it will change. It's no longer uniform. Yeah, it's composite. Yeah, so once you remember these things, when you look at different circuits, you'll be able to know when not you could use ampere circuits. So let's recap the reluctance changes if the length of the core part changes. So like if I, for some reason, increase the shape to make it look like this, clearly you can see that the length of the flux part at the main diameter has increased. So therefore the reluctance will decrease, directly proportional relationship. If the area were to decrease, so for example, if for this material, if I were to draw it like this, so you notice in the cross-sectional area for this, it has decreased. So if that decrease is the cross-sectional area here, the reluctance will increase. And mu, this has to do with the material of the compound, or the medium, I should say. So cast iron, steel, and all those stuff, each will have a different permeability or a different reluctance to flux moving through it. Yeah? Once you remember those things, it will make sense. Right? And that's how reluctances change. Right? Nice. So that's an important equation. So, right. So the next thing on the list is our BH curves. So we're just going to these here. So let's go through this. Pay attention to this one. All right. So B, H curve, and something called the hysteresis curve are the same thing, just different portions of it. Yeah. So the BH curve, it is normally called the hysteresis curve, the magnetization curve. And the BH curve is just the curve that relates the flux density to the magnetic field intensity. Right, so the one that Sir will have introduced you all, so one that looking like this. We have like steel, cast iron, and all those stuff. And it have this type of relationship. B. So remember the equation, B is equal to mu H. Yeah, so if I transpose for mu will be B on H, right? So B is the y-axis and H is the x-axis. And if you find the gradients of the line, well, up to the, once it's in a linear region for most of it, it should be here. Once in a linear region and you find the gradient, you'll end up with the permeability of the material. Yeah? At the saturation region, different stuff does happen, right? But you understand the saturation region just. But there's a BH curve, meaning if Sir give you a BH curve and he tell you the field intensity of a material, you're supposed to be able to get the flux density another way around too. Yeah, so something to keep in mind. So if he give you this on an exam or a midterm, and he give you either the field intensity, or if you could calculate the field intensity or the flux density, and you need the other one, you could use the BH curve to get it. Yeah, most of the time they will like tell you given or using the BH curve. Yeah, so if you say using the BH curve, that means you had to use the BH curve to get something, right? And to use the BH curve, you either need to have the flux density B or the field intensity H. Yeah. So once you have one, you get the other one. So something cool to keep in mind. And this here works on this equation. This B is equal to mu H equation. Yeah. So that's something cool to remember. All right, let's go try and see how this thing does, right? All right, so let's go. So B, as I said, is the magnetic field inside the core. So that would have called B. And H is just the magnetic field outside of the core. So that is really how it does note it, right? So let's go through this one. So we have our core. So the core is the box inside, right? We have a coil, and we have a source, a DC source. Right? So I'm gonna explain how the magnetization of a core does work, right? So we know these boxes, the rectangular boxes inside there, they are called domains. Right? Inside the domains, they have dipoles. And those dipoles, think of the dipoles as millions of lines, or you could say like lines like these. And in the domain, all of them are aligned in a certain direction. So you have millions and millions of them within different domains in the material, and they all point in different directions. So you might have like a material like this, and you have the domains are normally not like rectangular or uniform. They look like this. And inside there are millions and millions of arrows like this, and they all point in the same direction in the domain. Yeah? So for simplicity, I just gonna put one arrow, just for simplicity. So one here, So just for simplicity, they all point in different directions. Once you're within the domain, the dipoles point in the same direction. Yeah, so we have this. Yeah, and how magnetization works is when the dipoles are aligned in the same direction, you will have a stronger magnetic field. Yeah, so the magnetic field inside of the core is normally way stronger than the magnetic field outside of it. Hence the reason why we use a core. Yeah, because it gives us a stronger magnetic field density or flux density, as you normally say. All right, so let's go through this material. So initially, let me say we had a switch. Let me say the material not connected to the source. So since the material not connected to the source, dipoles are just disorganized. Yeah, all over the place, if not aligned. Some of it may be aligned, but like you say, in an ideal situation, the material, which is a ferromagnetic material, is not magnetized. Yeah, not magnetized. All the dipoles pointed all over the place. Yeah, so on our BH curve now, so we could start plotting the BH curve. So this is B and this is H. So since we said the material is unmagnetized, therefore everything starting from 0. Yeah, so now let's say we pull this down. So now the circuit on. Yeah. So current will flow in this direction. Yeah, and it will go through, go down, go down, down. It will flow and come back around. Yeah. So due to the current flowing in the coil, a magnetic field is produced. All right. So everybody know how the magnetic field does look. All right. So it looks something like this. Yeah. In reality, there's millions and millions of these. All right. But for now, it's gone, right? Right. So, right, so we have a magnetic field. So when you have a current in a coil, you have a magnetic field. Right? So what happens now is that as that current or the magnetic field starts to increase, as the current increase, or as the field intensity increases, the magnetic field inside the core will increase also. Yeah, so the more aka, the more current I have, is the more flux I have, and the more flux I have is the more flux density I have. In simpler terms, think of H as the flux outside of the core, yeah, which is what the dipole will align to, and think of B as the flux density or the magnetic flux inside of the core. Yeah, so H will influence B. The stronger H's or the higher H's is the stronger B will be. And B is caused by the dipoles aligning in the same direction as the magnetic field outside of the core. Yeah. So initially it have nothing. So as the magnetic field stays there longer and longer for an extended period of time until infinity and beyond, this H here will start to increase. And because H increasing and H is there, the dipoles will start to align. Yeah, so what happened is all these blue inside of here, it will start to align any direction of the magnetic field. Yeah, it will take a long time to do it, right? It wouldn't be like instantly. It will take a long period of time to happen. Yeah, and we know the currents, it will take a while to build up. Yeah, because the coil will resist it for a period of time, right? So as that current start to increase, the field intensity start to increase. So as I increases, you have your H starting to increase, right? So let's draw that. So as H increases now, what will happen to B? B will also increase. Why B increasing is because as H increases, the dipoles will feel a stronger urge to align with the magnetic field outside of the material, right? So it will look like this. It will start to increase. Yeah? It will start to increase. So as I start to increase H, B will increase. Yeah? So after someone draw how that will look in the material. So draw here. So after a long period of time, all the dipoles will align with the magnetic field. Yeah? All of them align. So the material is fully magnetized. Yeah? At that point, it don't matter how much I try to increase the current or how much I try to increase the field intensity outside of the core, this B not gonna change. Okay, you have no more dipoles to align. Yeah, remember the dipoles alignments is what going create a stronger magnetic field or magnetic density inside the core. If the current are increasing infinitely and you have no more H increasing, the B can increase, can no more dipole. So what happens is you reach a region where it's saturated. So no more increase in H will cause any more increase in B. So it's out of saturate. Yeah, so you reach a saturation region. Yeah, this right here, up to this point here, is what you will normally call a BH curve. So you have a linear region and it have a saturation region, which looks like this. Yeah, so this is the BH curve right here. But now we're going to do something called a hysteresis. So the BH and the hysteresis, they come from the same thing, the same graph. Yeah, so we have this point here, 1 and 2. All right, so let's go through. So now we can do some stuff to this stuff. So at this point, the material fully magnetized. It can't go anywhere else. Yeah, but what happened? What happened? If for some reason this battery, if I added like a rheostat or something, if I started to decrease the current, yeah, if I started to decrease the current, so the current started to fall, so the current I started to decrease, yeah. So because I will start to decrease, yeah, H will start to decrease. Yeah, and if H decreasing, B will start to decrease, right? But remember, the material is a ferromagnetic material, right? So like if for some example, I come and I pluck out this wire, I bust the circuit. Yeah, so the current can drop. Yeah, so therefore, if the I go to 0, H will go to 0. But the funny thing is, B will go to 0. Why? Because the material will maintain some magnetization. Why? Is because remember, it will take a long period of time for these dipoles to realign. Yeah? So after I cut the current off, some of the dipoles may go back to being unmagnetized, meaning it points in a different direction. Yeah, so some of them may, yeah, they would change direction. That is okay, because it have no more external magnetic field for it to align in. Right? So that means the material will maintain or will hold some level of magnetization or some level of flux density. Yeah, so the material will hold some of it. Yeah, so because of that, we know we H supposed to go back to 0. But then this is how the material will look. So at there, it will start to go back, it will start to decrease. It will start to decrease, but it wouldn't increase upward. So let me see how bad I could draw with this materials. So it will start to go back and it reach that point. Yeah. So H is 0, but it will still maintain some magnetization. Yeah. So this here is a point. Yeah. Who is the force? Yeah. It will maintain some magnetization. Now there's something for you to remember. Yeah. When the current change like that, the material will maintain some magnetization. It won't just go back to being unaligned. Just so. It will maintain some of it. Yeah. So let's remember that. Nice. So let us say B is still high and we want to demagnetize the material. Yeah? So in order for us to demagnetize the material, let us say we connect back up the circuit. Yeah, so let's say we want to demagnetize the material. First to demagnetize the material, we notice that we're here and we want to reach here. Yeah? To do that, we need to realign or we need to unorganize or send it back to being unorganized. Yeah? So to do that, we add something called a back current. Yeah? Because remember, we want the H in mathematical terms, we want the H to go in this direction. We want it to go to 0. Yeah? Because the H had to go this direction for B to come back to 0, right? So you add something called a reverse current. So that's reversing the polarity of the battery. So this will be the minus, and this will be the plus. Yeah? So when you add that, and you play it on for a period of time, the dipoles will start to go back to being unaligned, right? Yeah? So all of them will just go back to being unaligned. Yeah, let's go back to being disorderly. Yeah. After a period of time, it will go back to being 0. So you have no magnetization inside the core. Yeah. But you still have a field outside. It's just a reverse or opposite of what was given before. Yeah. So now at this point here, we still have the back current. What if now we leave the polarity of the battery as it is now? Yeah, so after a long period of time with this polarity, the same thing will happen. It just will happen in the opposite direction. So watch it. So all these dipoles here now go and realign, but they will realign in the opposite direction. So let me just redraw my magnetic field. So the magnetic field now will point in the opposite direction. Okay, reverse everything. And now the dipoles will point in this direction. Yeah, so they say after a long period of time, all the dipoles align. Yeah, so it's basically the same thing, but in the opposite direction. So the curve will start to increase up to maximum. It will start to saturate. Yeah, the saturation means that all the dipoles are like, that's what it means. So at its maximum flux density, it cannot hold anymore. It cannot be more of a magnet at that point. It can be more, literally at its capacity to be a magnet or to be magnetized, right? And the same thing as you did before. What we're gonna do, for some reason, we break the circuit. Power, flux, the current go to zero, or in layman's terms, what happens is you just go and reduce the current, yeah? So if you add a reverse current, what will happen is after a period of time, the current will go to zero and the intensity will go back to being here, zero, right? And it's the same thing will happen. If you wanted to remove the magnetization, same thing as before, you go and add a back current. So basically now we're going back to how the polarity of the battery was before, which is the back current. So positive here, negative here, and you add the back current after a period of time with that connected, it will go back to being zero and the pattern will continue again. If you leave this on for a long period of time now, all these dipoles go and realign in this direction, and after a long period of time, it can reach a point where it magnetized, it can't magnetize anymore. And if I add a back current to that, or if I break the current, break the circuit, it will go back. So like you say, we add a back current, it will start to decrease up to a point. It will maintain some. So when the current go to zero, or when it have no more field outside, when the current there, it's dead. So you have no more field outside. Remember, H is the field outside. Yeah, so if I cut off the current, it have no more field outside for the dipole star line too. Yeah, that's what it means. Remember, H is the field line with the flux outside. Yeah, that is what the dipoles are lining with. So if my I go to zero, I have no more current, right? H will have no more magnetic field outside the circuit, which means it have no more flux or flux density outside for the dipoles to align with. And because of that, some of the dipoles will go back to being unaligned. Yeah, but some will stay aligned. And that is why I have this point here, meaning the flux density inside the core, some of it will be maintained. It will basically maintain some level of magnetization. It wouldn't just go back to being unmagnetized. It will maintain some. It will hold it. Yeah? So after if I cut it off, it will just go down and it will stay. Some will stay. And now if I connect the circuit back up again now, the same thing will happen. If I connect it in a back current or reverse current and I leave it on for a period of time, it will just go back to being unaligned. And if I leave it on now in the same direction, the same pattern will happen. And this just happen over and over and over and over and over and over and over. Yeah? All right, that is how it does go. So without the red parts, so you say up to here is what so will give you all as the magnetization curve without this piece too. Yeah, so this here is what you known as a hysteresis curve. Yeah, this is what a hysteresis curve does look like. Yeah, so if let me just draw that back up to finish it. So that is one cycle. Yeah, so that one cycle why it went up, you drop the current, you increase the current in the opposite direction, keep on increasing the current in the opposite direction, you reach a max flux, so it saturates. Yeah, and after the saturation now, we do the same thing, we cut the current, go back, maintain some, and you keep going the current in the opposite direction, and it's still gonna happen. As the same idea that going on. Right? So this is what you call a hysteresis curve. That is all that's happening in the material. and it's due to the dipoles on it. Yeah? So the area, if you want to get the area inside of this material here, or this curve, is where it will call the hysteresis losses. And its losses that will be depreciated or dissipated in heat. So if you literally touch the core, you'll feel hot. Yeah? So eddy currents is basically like circulating currents in the material. All those things will be part of the hysteresis losses. So hysteresis losses plus the eddy currents losses will give you the total losses in the core. Yeah? So the area in here is what you call hysteresis losses. And if Sir asks here, what will it look like, or what will be physical representation of hysteresis losses? Heat. It will be dissipated in the form of heat. Yeah? So it's hysteresis losses. Yeah? And that is basically how the BH curve. So this here is the BH curve, which is basically one piece of it. So it's basically went from here to here to here. I'm gonna put it in green. So the hysteresis curve is from here to here to here. The line out one is the BH curve. Yeah, so if I draw it over, basically just this. That is the BH curve. Yeah, but when they start to talk about the hysteresis, is where you're starting to continue the pattern in the upward direction. Yeah, and you get one nice loop coming back to where you originally start. Yeah, that's keep the pattern really and truly does keep on and going over and over. Because for AC current, the current will be constantly switching direction. Yeah, so this here, the same pattern being repeated according to how much what the frequency of the oscillation is. Yeah, so this can keep continue going over and over and over and over. Yeah, what this will show is that it will never reach back to here, to zero. If you notice, it never reach back. Yeah, why? Because the core understanding of this is when you remove the current or when you remove the external magnetic field, the material will maintain some level of magnetization. Why? Because some of the dipoles will still be aligned. Yeah, once you have a set of dipoles in the same direction, you have magnetization. That's how a magnet does work. Yeah, and that's the BH group. So hysteresis and BH. They in itself the same graph, come from the same graph. Yeah. So I can say this is a BH curve, but you wouldn't really say call this a BH curve. You call this a hysteresis loop or hysteresis curve. Yeah, and this here, you would call this a BH curve. Yeah, so no the difference. Yeah. That is something cool that has happened with magnetic material. And there's the foundation of transformers and stuff. Yeah. If you're asking what ferromagnetic material is, so remember you have different type of magnets, right? The ferromagnetic one is if you magnetize it and you remove the current, it will maintain some material when you magnetize it and you remove the external magnetic field, it will just go back to not being a magnet. So this one is one where when you remove the current, it does not go back to being unaligned. Yeah? Because if you have a transformer, right, and you add a current to it, you put a coil and you add a current to it, you generate your magnetic field. And we all know how the transformer does work. When the flux from the primary coil cut the coil in the secondary, you have a EMF being induced in the secondary coil, and that will produce the current, and you get the step up or the step down transformer, right? When I remove the current in the primary, I do want to still have a magnetic field in my core. I want it to go back to being off, neutral. So you normally use a ferromantic material. So when I remove the external current, the field will go to zero. It will disappear, which is what I want. I don't want flux of fields in my material when I cut off the current. Yeah? So that's something to remember. So you all look at this document, so don't worry. Alright, so I go back to this. So air gaps. So briefly spoke about it, right? So what air gap is, it look like this. So you have a material, as you can see, the outline, the main part, which is not really mean, kind of look weird, but this piece here is the air gap. Yeah, see, there's literally a gap of air. You cannot use Ampere circuit although in this circuit. Why? Because it's not a closed loop. You have a space. Yeah, so you can't just use Ampere circuit although just over this. Yeah, so that's your one. That's how an air gap is. Okay, air gap. So when he has to talk about air gap and then you should have an understanding of what exactly will look like physically. All right, so some laws with air gaps, and there's something to remember. Once you remember this, trust me, questions will make sense, or it will be easier to do, right? Practically, the same flux is present in the magnetic core and the air gap. So basically, what happens is I have a core, yes, I have an air gap, but I still want flux to flow in the circuit or in this magnetic circuit. The funny thing is, the flux, just because of this air gap here, it will take a lot of MMF or magnetomotive force, the driving force, to send flux through this air gap. You need a lot. Remember, air is very resistant to flux, very resistant. So you have a very high reluctance. Yeah? So because of this reluctance here, it will have a very high MMF. The MMF is just the driving force. Yeah? The force you need to drive the flux through is similar to voltage. Yeah? The voltage will drive a current in the circuit. The MMF will drive a flux through the magnetic material. Yeah? So this MMF here really and truly, the core itself, the flux you need to go through the core when you're doing calculation will be significantly smaller than the flux you need to go through the air gap. So what will happen when you do the questions is that when you calculate everything, you add it up, the flux needed for here, because of this air gap, it will have a lot of flux going through the core material itself. Why? Because you need a lot of MMF to go through here, this air gap. Yeah. So once you add an air gap, just expect a very high MMF when you're doing the calculations. Yeah. Because the reluctance in the core will be very small compared to the reluctance in the air gap. Because the core in itself will be more susceptible or more accepting of flux going through it than air. Yeah. It's like trying to put a mango in air and trying to put mango in water. Like, why would you try to put the mango in water? Mango not going to go anywhere. Think of that as air. Not going to go anywhere. I think of the mango as flux, water as air. It's not going to go very far. But if you try to throw the mango in air, it will go far. Think of the air as the core, the magnetic core, the iron, or whatever material they use. All right. So, as we said before, the flux is the same. Yeah, in the air gap and in the core, right? So to maintain the same flux density, the air gap will require much, I said this already, high. So two things here more from this question. This, the same flux density, remember this. So the B, or the flux density in the core, is the same as the flux density in the gap. I cannot stress this enough. Once you remember that link, is something to remember and it'll make doing questions easier. Because once you have B, trust me, once you have B, you can literally go anywhere in this course. B is a very important value to have. Yeah, because if you have B, you can get H. And if you have B, you can get mu. If you have B, you can get flux. If you have B, you can get the magnetic energy. If you have B, you can get the inductor. You could go anywhere you want. Yeah, so, and look at that. I just tell you that the B in the core is the B in the gap. So if any question they give you the flux density in the core, you already know that it's the same flux density in the gap. Yeah, so that's something to remember. Look at that, right? So I go through some equations now. So because the air gap and the core is two separate entities, but they both sum together to give you the MMF, right? We know that the reluctance of the air gap will be different, right? The reason for it is R is equal to L on mu 0, A. Right? In most materials, like if we go back to this here, the A or the cross-sectional area for the air gap is the same cross-sectional area for the material itself. If you look at it like that, right? So A is the same. But the two things that will be different is the L, the length of the air gap. Yeah, this length of the air gap here will be different, as you could see. It will have like a small amount, like millimeters or something like that. Yeah, mu 0. Why using mu 0? Because you can't use mu r. Yeah, remember, you're in A. So the permeability at A is mu 0. Yeah, nice. So that is how you can calculate the reluctance. due to the air gap being there. Yeah? Because you had to treat them separate, or the core circle. Yeah? And the same thing for the gap. That's what I wanted to write. Yeah? So LC and LG, they are related. So if I go back to this on top here, right? When you're trying to get, and look at it, right? If I want to get the LC, or the length of the core material, right? Let's say from here to here is 20. And it's square. It's a square, right? So therefore this here will be 20, this is 20, this is 20. And from here to here is 20. Yeah? What if I said the length of this air gap here is like 2? Just 2. I ain't getting no unit, just 2. Right? If I wanted to get the length of the core part, which is LC, right? This is 20, so it'll be 20, 20 here. So I'm going in this direction. 20, 20 here, which is good. Here now, right? Well, so I'm going down here. You have to subtract the length of the air gap from the length of this piece here. There's just a sketch, right? So you have to subtract it from here. Come on, where's LC, which is the length of the core part. Yeah, the length of the core part is not 20 here because you have to subtract this air gap length here. So you actually get that's 18 and the 20 from at the bottom. Yeah, so when you're looking for the core part, you have to subtract the length of the air gap from it. Yeah, we want core part, which is the actual metal core of it. Yeah, not the air gap. You have to subtract. So when you're doing your lengths, reluctance or whatever need you be, just remember if you have multiple air gaps, like if you have 5 air gaps, and you want a length of the core, you have to subtract all them lengths from the LC. Yeah, so let's remember that. All right, but that's a correct at points. So otherwise, to be doing the wrong thing. When you're doing the maths, I would just assume you're good in maths, right? This here is the main diameter of the core. Yeah, this line here is incorrect. How to sketch it, right? They did say mean core length, so when you're reading it, you'll see. Yeah, so this is how it will look at the main diameter. When you're doing your maths now, I said this is 20. Yeah, but mathematically and geometric wise, that was wrong. Well, let's just see that. Right? For me to actually get this length here, they need to give me this distance here. Yeah? They need to give me these. Because if I have that, watch it. So like I said, this was 10, right? And square, so this is 10, all these are 10. Yeah? And I wanted the length of the square part. From here to here is 10, right? So half will be 5. Yeah? Half will be 5. Yeah? Half will be 5. So the length, like I said, this piece here is A, this piece is B, C, and D. Yes, the length are A. So this here, 5, right? Up here is 5. So it actually just be 20 minus the 5 from on top, the piece from on top, minus the piece from the bottom. Remember, we're going from half of the bottom piece up, then to half of the top. So you have to subtract what you don't need. So the piece that I don't need, I'll put it in red, is this piece here and this piece here. Yeah? And this piece here is 5, this piece here is 5. So the actual length of the core part of this piece of the material here, which is A, would just be 20, subtract the 5 from on top and the 5 from the bottom. So you actually get 10 for this here. Yeah, what you're seeing now is since the material is uniform, B will be 10, C now will not be 10. Oh yeah? Because C has the air gap in it, right? So C will be 10, which is basically from here to here. Subtract the 2 from the air gap. Yeah, so it actually be 8. So let's remember that. And well, D will be 10 because, sorry, that's uniform. Yeah, so I wanted to see that. So we're doing the LC. So the total will be LC, will be your 10 for A, plus the 10 for the B, plus the 8 for C, because you have to subtract the length of the air gap from the length of the core, because the air gap is not part of the core, or part of the length of the core. And plus your 10 there, adding up all of that, you'll get what? 38. Yeah, and that is how you will get the length of the core. If you want the length of the air gap, the length of the air gap will not give you any question. Yeah, might be 1 millimeter or whatever, they will give it. Yeah, they may or may not give you. But if this, let me say, they give you the total length of the core part. So let's say the total part, for some reason, let's say the total part, meaning total part, which is including the air gap length. If they say the total is like 40, and for some reason they give you the egg gap length, well, you could get the core part by the subtracting. Yeah? So you have to read the question properly. They may say the length of the core part, the length of the gap, air gap, or they might say the total length, yeah, of flux going through the material, which will include the air gap, the length of the air gap. So just be careful when you do it. LC, gotta subtract LG. LG they'll normally give it as a flat amount. Yeah, so I'll leave this sketch here when I give you the document, right? All right, nice. So this equation here came from one of our lovely equations on top here, right? It came from this one here. Yeah? So you can't use Ampere circuit to allow flat out because the L will be different and the H will be different. Yeah, it's H is really the reason why everything will be different. Remember, B is equal to mu H. So therefore, H will be B on mu. So we know B is the same for the air gap and the core, which is good. But this is what changes because for the core, the mu will be mu 0 by mu R. Yeah, so if you all didn't know, that's mu is mu R relative permeability of the core by mu 0, which is the permeability of free space, right? So for the core, you have mu. Yeah, so HC is the core, but HG now, you have the B, which is the same, which is okay. And you are divided by mu 0. Yeah? Because relative permeability is whatever the permeability of the material or the medium divided by the permeability of free space, which is mu 0. That is what relative permeability is. The relative to free space. But mu R for air, the medium is mu 0. And we're relative to mu 0. So mu 0 is 1. So therefore mu R would just be mu 0 for free space. Yeah, so that is why for this one here, it's just mu 0. But relative to air relative to air is just 1. Yeah, because mu R is the medium permeability divided by the permeability of free space. Yeah, so for the medium, like for iron and stuff, we'll have a difference permeability of the medium. That's where you have a different yeah. But for air, it's gonna be 1. So this equation here, this piece here will just be 1 for air. So that's where mu will just be mu 0 for air. So HG is this. And because of this occurrence, you can't just use this Ampere circuit alone. What I mean by use Ampere circuit alone outright is that the equation LH is equal to Ni, I use that just so flat out. Meaning I have one L, H is the same, N and I. But for air gap, it's different, it changes. Because you can clearly see they have different H's. So how you will look at it is that think of when you had like, if you didn't have the voltage of a circuit. So that's how I used to think of it. So let's say I have a circuit, a resistor, a resistor. And let's say it have a source. I don't know what the source is, but like we say I know the voltage drop across this is 3 volts, and the voltage drop across this is 2 volts. Yeah? And I can add the voltage across here and get the voltage of the battery. It's the same idea here. So when you use an Ampere circuit alone now, remember Ni is like F. Yeah, that's why it's important to know your circuit. So we say Ft, yeah, is equal to H L, or say Hg, by the length of the air gap. Yeah, so think of this as the air gap plus Hc, which is this is the core, the reluctance of the core, by the length of the core part. Yeah, so you had to add it up. Okay, and that is really what going on. You had to add it up separately. Yeah, from this row equation here, they could go anyway. If that asks for I, you know F is Ni. So you got Ni, which just be Hg, Lg, plus Hc, Lc. And this law will apply to, like, if you have different core materials. So, like, if you have iron and cast iron and stuff, you'll have to split up the HLs with respect to the material. So, what I mean by that is, let's say I have a core here. Let me say with the blue piece right here, this is iron, right? And let me say the purple piece. So, let's say the yellow piece here. This is cast. And the rest is steel. Sorry. Right? You can clearly see they have three different materials here, right? So what happens is you can't apply Ampere circuit law flat out. Why? Because you have different material. Yeah, so you have a core part here, you have a next core part on the next side, change the color, and then you have a next core part from here to here. So you have three, so you have L1, L2, L3. Each of these material will have a different H. They all will have the same flux density. Yeah, the flux density is constant, really. Yeah, but they'll have a different permeability. And because they have a different permeability, they will have a different um flux or field intensity, H. Yeah, that is why you just can't apply Ampere circuit law outright because you have to sum the different pieces together. So for this piece here, Ft, which is the total MMF needed to push the flux through this material. So like if I apply a coil here, weight coil, so plus minus F. So you know F is Ni, number of turns by the current. Yeah. So the flux or the MMF, sorry, needed to push flux through the circuit, which is basically through the different materials. It will be H, we'll say HI, Li for iron, plus HC, Lc for the cast, plus HS, Ls for the steel. Yeah? And that's how we'll calculate it. Sum it up differently. So go further now. For the question, they will give you relative permeability of the different cores. So like we say the same mu I is like 1,000. Like we say mu C, they say it's 500. And like we say mu S is 1,200, right? You may be asking how we'll calculate this by using an equation, right? So B is mu H. Yeah. So like we say in the question, they gave you B. Or they probably gave you H of the entire core. But well, that would be different. If they give you the H for each material, they could use the BH curve to get the B. So that's a little more complicated, but most of the time they wouldn't really ask you that. If they have to give you a BH curve question, most of the time it'll be one core material, just to make it easier. But you could use it for different material, right? If they give you B, you can calculate the H for each of them. Yeah? So anyway, so back to here. If you want to calculate the H here, this mu, you can replace that with mu R by mu 0 H. Yeah, because I want units. So if I wanted to calculate H now, since you know that the B is the same for all pieces, because the same plug density going through everything in. Even if it had an air gap, it will be the same B. Yeah? So remember that. So if I just transpose this for H would just be B over mu R by mu 0 by, oh, that's it there. No more, no by. That is it. Yeah? So now when you do any calculation now, you have HI, well, let's be B and mu R for the I, relative permeability for the ion by mu 0. HC will be the B, which is the same, divided by the relative for C by the permeability of free space. And HS will be B, which is the same, divided by mu R for S by mu 0. Yeah, and I say all our calculate. Yeah, so I hope you'll see that. And by now you should know how to calculate the length, say, core parts for each piece. It should be sent to the material, or most likely will give you some like values for the distances, the little maths, H's. Yeah, and from here, as I said before, if the answer for the currents, F is Ni. So after you do this, you just divide all this by the number of turns, and just so that you get the current. Yeah, and you can just go on and on and on. So as I said, if you have an air gap, you have to split it up. So you have a HC and your HG, right? So that's the I wanted to get through. So that basically where I got this from. The basic got it from Ni is equal to phi R. We know flux is the same. If B is the same, flux is the same. Yeah? So therefore, this R is just a RT, and the RT is just the reluctance of the core plus the reluctance of the air gap. Yeah? Because flux and B is the same. Because, what is right? B The flux is BA. You should know that by now, right? So if I transpose B, would that be flux on A, right? So if I transpose into A now, we have flux over A for the core is equal to the flux over the A for the gap. Yeah, most of the time, it have no reason for your air gap to be a different cross-sectional area. That don't make any sense. Yeah, so your air gap will be have the same cross-sectional area as the core itself, right? So these here are constants. Yeah, so because they are constants, you can just remove it from the equation. They're not going to change. So therefore, the flux is the same also. Yeah, because if B is the same, flux will be the same. Yeah, so something cool to remember, right? So that is why, but this piece now, that's where they get this equation. So that's for the flux, they just transpose for the flux and they get this equation. Yeah, so that's what going on there. Well, I already showed you this one with the sum of the intensities. Yeah, so it all depends on what the question give you. Yeah, that is what all this will depend on. Yeah, so once you know where you're going, you could pull it apart, right? And I already told you, flux in the core is the flux in the air gap, right? So now something cool that you probably, and I'll show you the MMF will depend, the MMF really going to depend on the air gap, because the reluctance for that air gap going to be real high. Yeah, the MMF you need to push flux through that air gap going to be real big. Yeah, so if the core was just core alone, well, metal, let's say cast steel, the MMF you need to push flux through that will be small, because the material already like getting flux sent through it. But from the time you add that air gap, whew, that MMF going to go up real plenty. Yeah. And when you do questions in class and stuff, you'll realize that when you actually calculate the reluctance of the air gap, it'll be real big. And when you actually calculate the reluctance of the core, it'll be small. So really and truly, the core reluctance negligible. Even if you left that out of the equation, the amount not gonna change by much. It's still gonna be real big. Yeah? Anyway, so fringing, right? So it have a concept known as fringing. So basically fringing is like in simple term, if I have a air gap here, right? So we know the flux will go through like this. Yeah, majority of it. But some of the flux will bulge outwards like this. Yeah, it'll satellite bulge out. So you have some leakage that going on. Yeah. So this phenomenon where you see in there is known as fringing. Yeah, so it's just the magnetic flux line bulging outwards somewhat. Yeah, the bulging outwards. Yeah, in normal condition, they will say ignore the effect of fringing. To reduce the effect of fringing, you could just make the cross-sectional area smaller. So make it like this. Yeah, it will just reduce it. But in normal operating condition, the effect of fringing is negligible. It's still there, but negligible compared. Yeah, because the flux in this piece here is way larger than the leakage that going on outside or the fringing. So in the questions, it's nice to say ignoring fringing. So it could be like, this man know what you're talking about. Yeah. So you could say ignoring the effects of fringing. Yeah, fringing. Yeah. So in normal conditions, this happens. Yeah, that's that. But you know that actually have some fringing or flux leaking out of the material. Yeah, and that is what going on. A fringing. So when you see it, that's what going on. All right. All right. So let's try a question. All right. So that's the last thing I wanted to do. Um, well, this one here, I'll probably do it next week. All right, but it's the same idea. All right. This one came for final exam. Yeah, but it's the same way. So let's see how fast you can run things. I'm not doing the maths, like the calculator stuff, and going through all that, right? We are engineers. Like, expect you all to be strong with your calculator stuff, right? I just showing you the steps and the equations. You can always go and plug in the numbers. So, yeah, just make sure you can with yourself the SI units and all these things, right? You can try the question home and you can send it to me and I'll correct it for you. All right. If you don't want to do that, it's have the book in the drive the students use, so there are similar questions to this, and that has the solution. So yeah, so you can check it out when you finish. All right, I'll send you the page in class. So let's go through this here. So we have figure one. The top is a square 4, right? At uniform dimension, meaning that here it's all the same, right? The uniform, right? The number turns is 1,000, so that's something to keep in mind. So it's 1,000, right? So x measures 10 meters. So if you go back, this here is 10, yeah? And then they said y is 2, right? So y here is 2, right? So good, going good, right? If the air gap, A is that air gap. So they said A, so you see in this air gap, this A is the air gap, right? And they said the length is 1 meter, right? So A, the length of it is 1 meter, right? Yeah, nice. So you're going good. Given that the flux in the tiny core is 10, oh, something good. So they said B is 10. And we know that the B for the core is the same as the B for the gap. Look, everything coming together. What else we know? We know the flux for the core will be the same as the flux for the gap. Look at that, everything coming together. All right, something to keep in mind. So I continue. And the relative permeability of the cores, right? So basically they tell you that mu R is 1,200. Yeah? If the effect of fringing is ignored, so we know what fringing is. So up here, you will have some flux leaking out. So we basically ignoring that, right? So that what fringing is, we're just ignoring that, which is most of the time what the question will require you to do, right? Right? And the flux moves to the main diameter of the core. Well, we know what that means. We know that the flux will, they already line it up for you. Main diameter, as the black part there, in the center. Yeah? Everything coming together now. Okay? Calculate the current in the core. Right? So, which is okay. Right? The first thing what I like to do is write down what they give me. Right? So, they give me B. Right? So, B is 10. Right? So, I think adding what's up? The permeability, well, it's just 4 pi by 10 to the 7, right? Like what mu zero is. I don't know if I don't think I added t with this one. Right? So I go back to the question. Right? Most of the time in the question, they will give you what mu zero is, right? So it's 4 pi by 10 to the 7, right? Which is a very big number. Right? So let's verify that. Yeah, 10 to the minus 7, right? Let's make it sure. 10 to the minus 7. Right, nice. Let's then make sure I right out. So that is mu zero, permeability of free space. All right, nice. So the one the current. All right, we know we cannot apply Ampere circuit law outright, but we know how to apply it because we know the N, we know I, so we know N is 1,000. All right, so we can say N I is equal to H T L T, right? Yeah, because you can't just use it outright, you gotta split it up. So we know that we can just add it together. So it could be H for the core by the length of the core plus the H for the gap by the length of the gap. Yeah? And that we're working now. So like going to calculate some stuff. So we need the length of the core. We need the length of the gap. We need the intensity of the core. And we need the intensity of the gap. Yeah? So let's go up and calculate that. So what we have? So we know X is 10, right? So X is 10. So therefore this length is 10. This here is 10 and this up here is 10, right? The length of the core part is 10. That's the dimension, right? So we know it's going to the center. Yeah, so center, 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 center. Yeah. So this is if this the height here is 2, this is 1, and this piece here will be 1, right? And there's 1, 1, 1, 1, 1, and 1, right? So looking at our distances, just like I did before, causes is a uniform dimension. Once I calculate for one, I could just use the same thing for others, except the pieces that have the air gap and stuff in it, right? So for this piece here, I need to subtract this here. I need to subtract this here from on top, right? Yeah, so it'll just be total length 10, subtract the one from the bottom and the one from the top, right? So you'll get 8 for this piece here, right? And it'll be 8 for here, and it'll be 8 for here, right? But here now, it wouldn't be 8, because you have to subtract the length of the air gap, right? For the core, right? So here it does be 8, subtract the 1 millimeter for the gap. So you end up with 7, right? Yeah. So the length, we know the length of the gap is 1, right? We already get that from the question, right? Length of the core will be a 8 plus a 8 plus a 8 plus a 7, right? So 8 and 8 is 16, 16 plus 8 is 24, 24 plus 7 is what, 31? So you get 31 meters. Yeah? So that's LC. So I go back into our thing at the bottom and plug in V. So we know LC is 31 meters, right? We know LG is 1 meter. So we have to get HC and HG. But we know that because we know the B is the same. So we know B is equal to mu H. Yeah? So therefore, H will be B on mu. Yeah? So you know the mu will change, but the B will be the same, right? So we can have HC. Yeah, would just be B on your relative permeability by mu 0. Remember, mu is mu R by mu 0. Yeah? Just remember that. Remember, right? Nice. So HC, you got that from the question. So in the question, now just be 10 divided by your mu R for the core. I think the set was 1200 and multiplied by the permeability of free space. Yeah. And then we have HG, B is the same, and it will be divided by mu 0. Yeah. So this will just be a 10 divided by 4 pi by 10 to the minus 7. Right? Just looking at the maths here, HC, you can notice that because you're multiplying this by 1200, you actually go and get a bigger or a smaller HC, sorry. But because of this now, 10 divided by extremely small number will give you extremely big number. Yeah? So you could clearly see that if you have to calculate the reluctance for this, the answer will actually be very big for the air gap of the core. Compared to the air gap will be small. Yeah? So nice. So we have majority of the stuff we need. So like plug it in. So I'm not gonna do the math. So I'll just write the, you know what, I'm gonna do it. That might take some time to write it in my calculator. So for your benefit. So we can have, let's calculate this one. So HC is 10 divided by open brackets 1200 multiplied by 4 pi 4 pi multiplied by 10 10 to the power of minus 7 close brackets. Yeah, so you end up with 6 6 6. So this is 6631. Let's keep it to whole numbers for now. Yeah, so 80. Right, so let's go back to the formula sheet to get the units. I haven't done this. So ampere turns per meter is the unit for field intensity, ampere turns per meter. Yeah. Right, I don't need to remember that. So I have to use that. So ampere turns per meter. Right, nice. B, Hg now, same idea. So that would be, let's clear this, 10 divided by 4 pi multiplied by 10 to the power of minus 7. Whew. Right. Oh, what's that? Let's go back to this one here. Open brackets, 4 pi multiplied by 10 to the power of minus 7. Whew, that's a big number. I don't know if I did. That's a big number. Just here, work it right in standard form. Whew. So that'll be 7.9 by 10 to the power of 1, 2, 3, 4, 5, 6 ampere turns per meter. So we can clearly see the difference. This one is 663. This one is 7.9 by that is 7.9 mega ampere turn per meter. This negligible compared to this. So your MMF really depend on the air gap. From the time you add a air gap, your MMF will go straight up. Yeah. So reason if you have like a core and you don't want to change the core material, you just don't. Yeah, because it's doing what you want it to do. But for some reason you want a bigger MMF. Yeah. So we could do instead of changing the core, you could just add a air gap. Yeah. Because depending on the air gap, you could control the MMF you need. Yeah, because the MMF for the air gap is very large. You cannot control it. So you have pump control. In most cores, you do have an air gap. It makes no sense. Because you don't want to be given so much energy. Because if you increase I, you have to get I and N will increase, huh? So you pull more energy. So you have to spend more money. Anyway, so back to our question. So what we have? We have each 663 ampere turns per meter. And this was 7.9 by 10 to the 6 ampere turn per meter. Right. So nice. So we have everything now. Now we can plug it in. So we know N was 1,000. I, we know HC, 663. We know LC, 31. Make sure, always remember everything had to be in SI units, meters, yeah, seconds. That's same, them laws still apply in these courses, right? 7.9 by 10 to the 6 multiplied by length here, gap, which is what? Yeah, so therefore, to get I would just be, well, add a plug calculator, so multiply that, so plus 663. So 7.9, then we have 1,000, so you gotta divide that by 1,000. Square this, so 7.9, sorry, by 10 to the 6, divided by 1,000. All right, divided by 1,000. All right, so 7.799. All right, divided by 1,000. All right, options. That's a big current. Yeah, that's the answer. Yeah, so that'll be amps. That's a huge current. Yeah, it's a very huge current. All right. So yeah, air gap. But I make up this question. I use meters in normal operating condition. Your air gap is extremely small because you can clearly see if your air gap is big, your MMF going to be real high, and because your MMF real high, you have a real current. Yeah, this is an unnatural amount of current. Yeah, because 1 meter air gap is real air gap, like real air you have to go through to connect the 2 points, right? So normally air gaps would be in like millimeter ranges, micrometer ranges. Yeah, because you could control that. Right, so we have I. Right. The second part, compute the values of the permeability and relative permeability of the core. Right, this piece here, not they could just state it. They said compute. So it just stated back to the question gave you. If the question didn't give you, so like if they said in the question that just gave you the permeability of the core, yeah, you will have to split it up. Right, so let me just yeah, so mu is mu zero, mu r. Yeah, so if they give you mu and you have mu zero, you get mu r. Yeah, so let's read, right, it's relative. Well, yeah, so this one will give you mu r. Yeah, so it cannot be redundant asking you to do it again. But in some questions, they will just give you the permeability of the core material, which is just mu. Yeah, so you have to read the question properly. If they just give you mu alone and they ask you for the permeability of the core, relative permeability of the core, now you have to use this equation here, transpose for mu r, so you end up with mu on mu zero, which you know already. Yeah, and I said I do that. And the last piece now, they said every air gap is zero. Yeah? Meaning that's no air gap. They find the current in the coil for the same flux density of 10 in the port. So basically what they're trying to say is tan omega. Yeah? So it have two ways you could do this, right? Remember for this equation we write here, we included this here. Yeah, and what we did to this LC, remember this LC, we had to subtract the piece of the length of the air gap from it. Yeah, so all we really do for this here is just for this LC. First of all, remove this because it's no air gap anymore. So this will go out. So this answer wrong. So now all I can do for the HC now, remember this, let's go back to the diagram. Remember this here 7. So if I add back the 1, so now it's just a 4. Now this piece on top here will just be your normal 8 that you had before. Yeah, so 8 4 is out 32. So your length now will just be 32. Yeah, so if your length is 32 now, this would have go back to being 32. The H not going to change. Yeah, because it says for the same flux density. Remember, B is mu H. Yeah, so HC will just be B on mu. B is the same and you already do this. So the H not going to change. But the L will change because now you're adding back the length that you subtract. Yeah, so this will just be HClC. So that'll be 663 multiplied by 31. And that'll be your answer. So I'm going to do that quick. 663 31. So it's 20. So 5, 5, 1. All right, and then you divide it by 1000. So divided by 1000. And you get, watch this, 20.553 amps. What it was before? It was 7,900 amps. Yeah, this is with the air gap. And look where it dropped to with just the core alone. You see how big that comparison is? Yeah, so your air gap have a significant weight or strength or determination where MMF will be and in turn your current. Yeah, so this was a nice question. It tested a lot of stuff. All right, so I'll show you how to work with the ampere circuit. I'll lost put in the top, calculating the L's, calculating the H's, told you what the B is the same, the flux is the same. If you want to calculate the flux of this, you will have to calculate the reluctance. But if you already have B, you can just get the flux. Yeah. So, because you know what A is. Okay, the cells are uniform material. So that'll be your 2 by 2, and you'll have put 4, and you already have B, so you'll have be 5 is equal to 10 by 2 by 2, which is 4, and you'll have put 14. Yeah? Or if they didn't give you, like we said, they didn't give you B for the question, the alternative to that is this equation here. Yeah? So if they didn't give you B, or for some reason you have a different variation of this, let's say you have Ni or something like that. Yeah, so there's a nice equation to remember too. All these here comes from the equations. F is equal to Ni, F is phi R, Ni, you could go anywhere. Once you know your equations, you could be able to go through and make sure you get whatever you want based on what they give you. Yeah, and just remember when you're using it for this is RT, so you gotta calculate the reluctance of the air gap. So it'll be Lg mu 0 Ag and plus your RC, which is your L for your core divided by mu for the core itself, which will just be mu 0 by mu R by the area for the core. And you gotta add these two together, plug it into here, and assuming they give you N and I, you can calculate the flux. Because the flux will just be an Ni over your total reluctance. Yeah, all these are equations, right? But this is what I wanted to catch. And that is the question from here. So going to the other stuff, but there's a good question to be able to do. All right, so next class when you come, I'll go through this one with you. We'll take it from there. All right, so stop the recording.